So I want to mention the rules that we have in today. The first rule is that you have 6 minutes to present your presentation, talk about it, and also have maximum of 6 minutes for Q&A session. And today we're presenting more technical part. So I gave you access. Can you share it?
Yeah, no.
Okay, can you please share it? I need to know. And then we'll start. Okay, are you ready?
Uh, 1 sec, please. I think we are.
Okay, your time goes now. Good luck.
Start,
Hello
please.
everyone. Our engineering advancing aerodynamic innovation. Our engineering philosophy was centered around one key objective, minimizing aerodynamic drag while maintaining structural efficiency. Instead of designing visually aggressive elements with excessive downforce, we focused on creating a streamlined body optimized for maximum straight line speed. The underfloor was designed to guide airflow smoothly beneath the car, reducing plastic drag and minimize flow separation. Additionally, real drag is through lightweight wheel geometry and optimized rotational efficiency.
Okay, so there are only four core design principles we used. First one was minimization of frontal area. Second one was building the profile around supporting structures. Here, also a compromise between weight, technical regulations, and also the efficiencies that we want, and managing airflow through design pathways. As you can see, here is the minimal accepted width of the support structure, and we created an airfoil around it to reduce drag. Specifically, we used NACA 0008 airfoil as we don't need as much lift, but we need to reduce drag, and it's symmetrical and it works for us.
If we talk about materials, material selection was based on manufacturability, structural reliability, and weight reduction. For aerodynamic and superstructures, we selected PLA filament. Unlike ABS, PLA can be printed at relatively low extrusion temperatures, allowing highly stable and precise manufacturing using our Bamboo Lab P1S printer. The main body was manufactured using the official STEM racing standard-based balsa wood plank. Balsa was selected because of its extremely low density and excellent machinability, allowing lightweight
Yes,
aerodynamic
thank you.
optimizing while remaining within technical
Start.
regulations.
Inspiration. So the main body of our car was inspired by the bird kingfisher. As you can see the side profile, the top rail was created by mimicking its shape, and the bottom one was created by using the NACA 0008 airfoil. The top view was created with the same bird, but with a virtual cargo uh, built around it. And the CO2 cartridge was as thin as possible, around 3.1 millimeter, using with the its width was 3.1.
Our wheel philosophy focused on minimizing rotational and aerodynamic drag. To reduce airflow disturbance generating by wheel rotation, the wheel superstructures were streamlined using an ACA 0008 inspired geometry. We integrated 4 by 8 mm bearing into each wheel assembly. Estimated rolling resistance, polymer wheel contact on a smooth stem racing track. Uh, Stem racing track surface is approximately 0.02, while bearing friction is approximately 0.003. This means the bearing system reduces rotational friction by nearly 10 times.
Front wing. Front wing has a really complex shape, so its main purpose was to make an airflow go around above wheels. And here's a cool feature of our airfoil. As you can see on the graph here, um, its drag on the -4 degrees is nearly the same as the drag on the 0 degrees angle of attack. And we chose it as on the -4 degrees, it creates more lift than neutral 0 degrees. So on the sides of the car, the angle of attack is higher, as you can see, and on the near the center is lower.
Rear wing and structural integration. The rear wing system was designed primarily for wake management and airflow stabilization. A slight curvature was applied to improve airflow continuity while maintaining minimal drag ingress. To further reduce wheel wake turbulence, we integrated teardrop-shaped structures behind the rear wheels. Additionally, the rear wing mounting system was designed as a modular structure, allowing rapid replacement during pit stop operation.
Manufacturing. Manufacturing was divided into several stages to ensure dimensional precision and structural consistency. The main body was CNC machined from the official bicep length. Multiply machining paths were used, road machining for bulk materials removal, semi-finishing for aerodynamic shaping, and final finishing for surface smoothness. Tool path optimization and adaptive clearing state strategies were used to maintain clean surface quality and accurate tolerances. A full-scale PLL prototype was also produced to validate rigidity and assembly before final manufacturing. Final structural design. Our final design combines aerodynamic optimization, geometry, lightweight constructions, and modular engineering principles to improve pit stop efficiency and several structures were designed to be removable and replaceable. The wheel support structures at rear assembly were modular, allowing rapid maintenance if required. By combining aerodynamic efficiency, mechanical optimization, and lightweight engineering, we developed a highly competitive stem racing vehicle optimized for maximum straight line performance.
Um, Basically, that's it. We are ready for the questions if you have any.
Great. So your time for Q&A goes now. Good luck with that one.
Thanks. Is there any questions? Maybe about rear wing or the front
Dear
wing?
judges, if you have any questions, that would be nice.
So these are the wheel supports.
Sorry, do you hear me?
Yeah, yes, I do.
Yes, okay. You say about the PLA plastic and you choose it. Why you choose PLA plastic?
So we chose PLA plastic because we already have a Pambula printer and it can print PLA very good. Unlike ABS, which requires a constant warm chamber, PLA can be printed almost everywhere. Also, it's very accessible. We can find it almost in every store that sells like filaments. And also, its printing temperature is relatively safe for all the participants. Also, it's reliable. That's why.
Where you use PLA plastic?
Okay, so we'll use it for the front wing. We'll also use it for the back wing. Basically, everything except the main body, because the main body will be CNC machined. Front
What
wing, the
material
back
do
wing,
you
all this
use?
teardrop.
CNC machine. What material do you use in the CNC machining?
Okay, so we will use the balsa wood as the original official stem racing block is made out of lightweight balsa wood. Yeah, we'll use it. We'll find it on the stem shop a bit later.
Okay. What about the forces? What kind of forces do you have on your car?
Forces?
Yes, forces. When it accelerates from 0 to 100, it's get a lot of forces.
Yeah. So you're asking the stress analysis. However, we haven't
Yes,
done it
stress
yet,
analysis.
but the prototype we printed here, actually it was like pretty tough. I think it would yeah, it could tolerate all the forces of the high acceleration.
Uh, do you think that the PO plastic can how to say handle the power of this one?
Yes, I do, because the mass is really low and it's good. Yeah, it's good.
Do you have any kind of analysis to improve this?
Actually, like we had a bit of calculations, but not the analysis. The calculations are not shown here, but they're in our Figma.
I don't see any calculations. I see maybe aerodynamics, but this aerodynamics was on your before slide. That was before your presentation. About new stuff. You will use carbon fiber or
Actually, we considered that, however, finding carbon fiber and also the resin to build it is a bit problematical. So I think we'll use only plastic at first and balsa wood. However, if we do find the right sources and sponsors, we could use the carbon fiber as well.
Mhm. What kind of CNC do you use to produce your car?
So it's milling. As you can see, the block will be placed near two holding pieces, and it will just cut off all the excess parts out of the whole block.
Do you know how CNC machines works?
Yeah, kind of.
Okay, what in what format you will give your hopefully your car to the CNC machine?
I don't remember the format. However, as you can see here, like we did the analysis and we could prepare the file in Fusion as I did previously.
Okay, so you have okay. Why do you don't have any kind of analysis?
Hmm?
Why do you don't have any kind of analysis?
Yeah, so there was the reason because we've made first this part of our car, and as you can see, it has a lot of details because it's like ready to be assembled, as we did here. However, all these softwares they require like simplified version of the car, and we didn't have time to simplify it just for the and only for analysis, because all these details, as you can see, there are a lot of bearings inside there. See,
Yes,
here's
but
another
for
example.
analysis, you shouldn't use the whole car. You just use your
I'm
chassis or your
sorry,
main
but the
body.
time is up.
Okay.
So that's it for Q&A. Thank you for your N92 RT team for presenting. Now we are having time for break.
Thanks for having us.
Right. They said today that they have technical part and tomorrow they will be presenting our enterprise part. And I think the team knows about that, right?
Yeah, we do know.
I said today in the beginning, they have technical part. Okay, great. See you guys soon.
Yeah, have a nice day. See you
Okay.
tomorrow.
Thank you. See you.
Bye bye.
Hello,
Oh,
we're hunting routine. You have
okay. Did you
Sorry, can you
turn off?
someone close your microphone, please? It's echo
okay,
here.
okay. Sorry. Um,
Okay, so I should give access, right?
mhm.
Okay, you have it.
Mhm.
Great. Okay, if our judges are ready, we can start the presentation. So today you have the technical part. Tomorrow you will present the enterprise part.
Yes.
And now I think judges are ready as well, so you have 6 minutes to present and 6 minutes for your Q&A session. So your time goes now. Good luck.
Thank you. Hello, dear judges. We are Hunt Angry Team, and this is our engineering portfolio. At the first, we do research. Our team studied Formula One aerodynamic to improve the performance of the STEM racing car. We used fusion and CFD analysis to reduce drag and improve airflow. The aerodynamic drag force was analysis using this equation, where reducing the drag coefficient and the front area help increase speed and efficiency. We also tried pilot reaction time because faster reaction improves the race result. Next, we develop and test 4 different front and rear wing design to improve the car's aerodynamic. Each version reduce drag and improve airflow and stability. After analysis, we select the fourth and final wing design because it produced the best aerodynamic performance with maximum downforce, minimum drag, and better high-speed stability and traction. Also, wind tunnel testing showed that the car has lower dynamic drag, stable airflow, and effective downforce, improve airflow and around the wheels, and underbody creates battery grip and stability, resulting in strong traction and high-speed performance. Okay, next.
So, hello, my name is Nagar, and I'm responsible for the engineering part of our team. And so, mainly, we focus on the lightweight construction of our car. The chassis were made 3D printed using PETG material, and the wheels were printed PLA for lower rolling resistance. The axles were made from steel wire to provide strength and durability. Next. So our main goal was to improve the aerodynamic stability and the efficiency of the car. We created several concepts and compared their performance after testing and evaluation. Design 4 was the best option because it provided the best balance between drag force, downforce, and stability. The car body has a streamlined and lightweight shape, which helps reduce air resistance and improve airflow. The nose cone and front wing direct air smoothly around the car and create front downforce for better grip on the track. The side pods optimize airflow toward the rear section, while the rear wing increases the rear downforce and improves stability at the high speed. The aerodynamic force was calculated using formula that you can see on the screen. And next. And our final results showed that a lower drag force of approximately 0.49 newtons, which demonstrates good aerodynamics efficiency. In conclusion, the final design is lightweight, stable, energy efficient, and technically optimized for high performance use.
Final design evaluation. The main design goal is to improve the aerodynamics, downforce, and stability of the car. The main components that have been improved are nose cone, a more streamlined shape, front wing, body, hollow, side pods, rear wing, and wheel support system. Overall, the design has been created to achieve maximum efficiency, speed, and sustainability. 3D modeling. The main goal was to create a lightweight, stable, and aerodynamic car design. We used Autodesk 360 to model the chassis, wheels, and bodywork. CAD helped us test dimensions, weight, and part fitting before 3D printing. The design process included sketching, extrusion, fillets, and final assembly. CFD analysis of airflows was also performed. The car had an estimated drag coefficient of CD equals to 0.9 with a target resistance with a target reduction of 5%. Low pressure zones behind the car increase drag due to the vacuum effect. Overall, CAD modeling and aerodynamic analysis helped improve the car's performance and save our time and materials.
We tested the front wing made of nylon 12 under a 2 kilogram load. It deformed, causing turbulence and increasing drag. By adding different ribs and performing CFD analysis, we achieved smooth airflow around the body without large pressure changes, improving aerodynamics before printing.
So, we finished.
Okay, great. So now you have 6 minutes for a Q&A. Good luck with that one.
First question, where you made your CFD analysis?
In Fusion.
Aerodynamics you made in Fusion?
Yes.
Can you show how it looks?
Yes.
No, it's 3D model, show me analysis.
Sorry.
Can you open
If you made analysis in Fusion, you can open it in Fusion.
Yes, it's
We
on
do
another,
aerodynamic sim scale system. Only aerodynamic in sim scale, but full 3D of cuts in Fusion.
Okay, so analysis of aerodynamics you made in sim scale.
Yeah, in sim
Yes?
scale. Yeah.
Okay, what is your drag coefficient? And the one question, you sent to judges your presentations that you presenting now, or because I'm opening this is not like your presentation that you're showing in your presentation now, the document that I opening.
Could you please repeat the question?
You sent to judges your presentation, but presentation engineering portfolio file, it's not like a presentation that you show us at the moment. It's different.
Yes, we have a separate engineering portfolio and presentation, but we can open our engineering portfolio too right now.
No. Why you don't send your presentation that you will pitch, or that you already speech it?
Because it is the same information like we have in our engineering portfolio. We just a little shortened it.
Here in the so in the it is the same. It's the CFD analysis. At the picture with analysis, they're not the same cars that you show us in the 3D model. The rear front wing is not the same. Which one is correct?
Let us show the correct version of our you mean our final design, right?
Yes, I mean your final design, and here you made the CFD analysis, and the page name of the page is the CFD. You find the center mass, okay, but I see a CFD analysis, and they make the aerodynamic. But in the aerodynamic tube, here is another 3D model, not your car.
This is the CFD analysis of our final design.
Yes. Yes, and open your first page.
First page?
Yes, your main design.
Engineering portfolio. Yeah.
This one is your main design, yes? This as a first page design.
Yes.
This one. This is your final design.
Yes.
But why rear wing is not the same as this CFD analysis model?
It's the same as in CFD analysis?
No. No. Open CFD analysis.
Do you see the screen right now?
Yes.
Okay.
And zoom it. Here, see the analysis. If you see your front wing, rear wing, and the rear how to say diffuser, it's not the same as your so in your final design.
Oh, it's our second design of model.
How to say? We asked
Maybe
you.
we
We made
our new model maybe.
we made a special video for you that we said is a final design. We should be CFD analyze it and make the manufacturing processes. Here you are. If you are not putting here final result, why you making showing us a not final result? And about manufacturing, here is not information about manufacturing processes. How you manufacture
I'm
your
sorry,
car.
but the time for Q&A is over, and we are moving to the next team. So, Hunter Green, thank you for the presentation.
Please answer the question in chat.
Okay, thank
Okay,
you.
about manufacturing processes, you can answer to the chat.
Okay, now we have a team Nomad Racers. Nomad Racers, are you here? Are you ready?
Hello, yeah, we're here.
Okay, can you share your screen?
Yeah,
Can
sure.
you do it?
Yeah, 1 sec. Wait, where is it? Is it?
Okay, can you do it now?
Yeah, I can.
Okay, great. Tell me when you are ready.
1 sec. Сейчас приму тебя. Do you see the screen? Dear judge, do you see the screen?
No, we don't see screen.
All right, 1 sec. Чего у меня тут нет?
Please be a little bit faster.
Yeah. Now you should
Okay,
see
now
it.
we're seeing the screen. Great. Okay, you're ready now, right?
No, wait. Can you give us like 20 seconds? Well, our camera is turned on, right?
What?
You see us, right? Can you see us?
Yeah, we see you. We see you.
Okay, yeah.
Okay, so you have 6 minutes to present and 6 minutes for Q&A session. So now your 6 minutes presentation time goes now. Good luck.
Hello, we're not racers. Our journey began at Kapchigai when we saw like a different nature and we got inspired by different animals and beyond there and beyond. So you'll see what I'm talking about throughout the presentation. Here you can see our team and you will see each of us contributing to the project throughout the presentation as well. So the timeline, well, the timeline is May when we do research. It's about regulations and general researching stuff. Concept design is about sketching and selecting the best concepts. July is basically CAD development, improving our mistakes. CFD is testing our card model on the computer, and then in September we're planning to manufacture and test the card.
Okay, here you can see our first prototype, VID Nomad Cut. Our team used Autodesk Fusion 360 to design and refine the race car for beyond edit testing. Our initial design suffered from excessive aerodynamic drag, limiting acceleration performance. As you can see here in this diagram, the front wing has very steep angle of attack. This caused increased pressure build-up at the front and the flow of separation, resulting in efficient airflow, which we will see later in our SFD analysis. Here you can see our improved V2 Nomad Cut version of our car. This design model achieved a drag reduction by 1/1000 newtons. This resulted in this was caused by replacing rear wing by spoiler and minimizing width of the car beyond the regulations. Smooth edges also result in a decreased drag. Here you can see our final prototype. Air is pushed both above and underneath the car. As you can see here, it is like fully following the regulations. The wheels have the smallest dimensions allowed in the regulations. This enables them to create less drag. This in the right, in bottom right corner, you can see the curve car. It is like very curved and does not create as much drag. During Kaptigai trip, we inspired by Cobra, and we did a lot of research to find most aerodynamic animals in the world. The wandering albatross, known for its unmatchable gibbon efficiency, it has the biggest wings, so we inspired by them and tried to copy them into our design also. As a stingray fish, it's sleek hydrodynamic with hole inside, which allow air to flow inside of the car and reduce drag. The head of the Cobra allowed was inspired to do rear wing, so it does not create drag and allow air to overcome it underneath the car.
So here's our V1 and V2 models. We basically achieved our V1 model was high angle rear wings, which was reducing the drag, increasing the drag. So after integrating the wing into the front chassis in V2, we achieved 32% reduction in drag. So next slide.
Okay, so coming to our models. So the first car our goal was to minimize drag for maximum straight line speed. So we started with the iteration one baseline with no side borders. So it hit a drag coefficient of 0.383. So it was slippery, but our velocity plots showed air breaking off the chassis and hitting the rear wheels, causing heavy turbulence. So, and our next iteration was so to fix this in our next iteration, we introduced two thin side borders. So this shields the internal components and cleaned up the wheel wakes. So as a result, the drag coefficient dropped by 5% and cutting total drag force to 0.317. And however, this rear flow remains unstable, so giving us poor stability rating. And finally, this led to our final design, iteration 3, by using thick borders. And we created a seamless aerodynamic aerodynamic channel around chassis to keep the airflow attached. So the results were breakthrough, as our drag coefficient were 0.32 and there were downforce, so giving us concerning grip while reducing drag.
So now, moving to our manufacturing, we combined two different methods to build our race car. We used CNC machining for the main body car, and we used 3D printing to get a perfect accuracy. This smart strategy gave us excellent build quality while letting us quickly test and change our aerospaces. So, we ran a few tests at home conditions, structural rigidity plus load distribution. The purple weight is 2 kilogram. Those two weight power banks is 0.5 kilogram.
It basically showed us how the structure was like rigid and it was good quality. And here we talked to a few teams. We got some advices from them. So Apex Racing Team.
Sorry, your time is up for the presentation. Now you have 6 minutes for your Q&A. Good luck with that.
Yeah, we're ready.
Can you show, please, your 3D model?
Of course. Which one?
Where is analysis?
Analysis.
It is here. What
This
at the bottom you can see the views. The view from the bottom, and here you can see the view from the side. We can see our model. We can say that
Do you
our
have rings?
Yes, here you can see that at the beginning and the end there is этот circles that will этот как бы канат.
Канат?
Да, ну типа трос.
Не знаю, beam.
Okay, that will attach to the beam. Here, first
Okay,
one.
and show please your analysis.
Что не бежать у тебя?
Что это? CFD analysis? V3?
Да, V3. We can show you our sim skill analysis if you want.
Ну, мы сейчас не...
In which SCAD software do you made it? And
In
did you make it?
Yes, we can show you.
SimScale.
It is here.
And we're drawing some of the parts in CAD, like the box.
It is like second part. It is like here. Can you see it? It is like we did.
And
like,
what is your final drag coefficient?
You can see it on the screen. It's 0.32.
Weight of your car?
It is written here. It is like calculations. We can show it in Fusion. We did calculations. It is about 48.3 grams, which is allowed. It is written here.
Okay. Next question: how do you make? How do you manufacture it?
Here you can see the table from Fusion with math calculations.
No. How you manufacture it? About manufacturing processes.
We are going to use SNC machinery and 3D printing for prototypes. After that, after we ensure that our prototype works, we are going to use CNC machinery and stem blocks to cut them and try to decrease the mass of the car, so it will in allowed barriers, but as less as possible, trying to придерживаться trying to remain mass of 48.
Okay. Next question. What about, do you make some kind of calculation how you cut? What the CNC machine do you use, or maybe what kind of 3D printer material in the printer you use on the
material plastic on our printers. Right now we're in our school lab and we just used our printers to print to print our prototype on printers we tested yesterday. Now we can show it to you. Она на сайте где-то стоит. Посмотри вон там справа. Сейчас он нас принесет. Here you can see our car. It was printed in our school printers from PLA material.
Can you show it bigger? I don't see it. No. Yes. What is the final size of, and it is in the final dimensions of your car, or it will be smaller or bigger?
It is 1-to-1 ratio of printing. It is fully aligned to regulations. its total length of the car is about 20 centimeters. The height is about 6 centimeters, including the spoiler and the rear wing.
Do you have another kind of analysis, maybe for the strange analysis?
Yes, we had, but it is in our portfolio. When we're going to send it to you, we can see it in our portfolio.
Yeah. Yes. Why you didn't see it yet?
Yeah, we will
Why
send it
don't
to
you
you.
see?
No, because
Okay.
you extended the deadline for us.
Yeah.
For the portfolio, as we have exams right now.
Okay. What the main body will be? How you will make your main body?
We're going to manufacture our main body from stem block. When that we're going to buy from Europe, and we are going to cut it in CNC machine. So in all three axes, Z, Y, and Z. So it will be as light as possible, contributing to our total mass of the car.
Okay. Is your file of the CNC cutting machines ready?
It is preparing right now. We are going to test it, I think, this week. We're going to cut it from wood, so to test our mind and our strategy for cutting in CNC machinery.
Okay.
Your time for Q&A is, sorry for interrupting, your time for Q&A is up, so that's it.
Please send your 3D model to my DM.
Okay.
Okay. Thank you.
Okay, next team.
Bye. Goodbye.
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 Okay, next team is... Okay, a Q team. Are they here? I don't see them in the waiting room.
Hello, we are Team Skyrus and we are ready to present.
Okay, great. I'll give you permission now. Okay, can you share your screen? So I want to tell that you have 6 minutes to present and 6 minutes to answer for the
Okay.
Q&A session.
So, can you see our presentation?
Yep, we can see.
Just a second, please.
Yeah, just.
Okay, ready?
Yeah, we are ready.
Okay, your time for presentation goes now. Good luck.
So, hello, dear judges. We are Team Skyrus from Kazakhstan, Shymkent. So, our engineering goal actually was to create our based on measurable performance, not only appearance car. So, our main focuses areas were actually mathematical modeling, wheel engineering, aerodynamics development, and precision manufacturing. So, let's move on to the next slide. Actually, before designing the car, we identified the most important factors. Our race model showed that car mass affects 41.7% of performance, aerodynamics approximately 30%, wheel friction 21.4%, and T-zag wide friction 5.9%. Therefore, our priorities were clear. So we had to reduce the mass of our car, reduce the drag, lower wheel friction, improve stability, and manufacture within plus minus 0.1 millimeter tolerance. Let's move on to the next slide.
And now let's talk about the mathematical race model, where I think that the physical testing was inconsistent because of the CO2 canisters created about 20% of variation between runs. And to solve this problem, we are used a Python code. The model included drag, mass, wheel friction, and the tether friction, yaw stability, and the CO2 thrust decay. It predicted acceleration, velocity, displacement, and the final race time. This helped us make decisions using data instead of trial and error.
Yes, and the next slide is wheel engineering. Wheel performance was important because wheel friction contributed 21% to race performance. And we used the formula I equal to mr square, meaning wheel inertia depends on mass and the radius. Using Fusion 300 VA under 1550 Newton load, we tested several wheel designs. And our final choice was a topological optimization wheel with peak stress 28 megapascal. And this gave us the best balance between strength, stiffness, and rotational efficiency. And the next slide is about aerodynamic development. Aerodynamic drag contributed 29% to performance, so CFD was a major part of our design wheels. The front wheels were especially important because wheel wake and the turbulence created a large drag source, and we used ANSYS CFD pipelines and the wind tunnel testing to check how airflow behave around the car.
In this slide, we will talk about prototype comparison. So you can see our prototypes, which we did prototype A, B, and C. So you can see drag force, lift, and mass model race time of each car. And also you can see our formula to calculating our drag efficiency. So prototype C was selected because it has the lowest drag and strongest aerodynamic stability. So our calculated drag coefficient was approximately 0.2099.
And manufacturing engineering. After design optimization, manufacturing accuracy became critical. Our target tolerance was 0.1 millimeter because small geometry errors can change airflow and reduce CFD accuracy. So we used Fusion 360 accessibility analysis to check if all surfaces could be machined. For CNC machining, we used tools such as a 6 millimeter flat end mill and planned additional side milling for difficult surfaces. And our principle was simple. The car must be fast, but also manufacturable.
And now let's talk about materials and our components that we use to create our cars. For the body, we used official F1 model block form. For the wheels, we selected Ketron Peak 1000 because it is stiff, lightweight, and suitable for precise CNC machining. And for bearings, we selected CMR 73C model that exhibit ceramic bearings. Their best spin time was 42 seconds and compared to 10 seconds for steel bearings.
So let's move on to our final validation and testing. Actually, our CFD drag was 0.2542 newtons, with the tunnel drag was 0.2743 newtons. The difference was only 0.0201 newtons or 7.3%. So our final predicted race performance was race time around 1 second, average velocity around 20.98 meters per second, and peak acceleration was 32.4 meters per square second. In conclusion, our car was developed through data, simulating, testing, precision manufacturing, and actually that's all for now. Yeah, thank you for your attention. We are ready to ask your question. To ask for your questions.
First of all,
Okay, great.
can we
So
show
now you have 6 minutes for your Q&A session. Good luck.
Okay, first of all, can we show our bolid?
So it will be on screen, okay?
Yes. Okay, let's first it's the Autodesk 5-axis CNC machine, and in Fusion 360 we try to simulate how our car will be manufactured. Just wait some minutes. And as you can see, it's the simulation of manufacturing our car's body.
I have short questions about manufacturing. Which material you use for your body?
As we said, for main body, we will use official F1 model block foam.
Block foam,
Because
okay.
yes.
You found where is you found 5-axis CNC and used it?
Can you repeat the question? I think it's a little bit unclear.
Oh, in Kazakhstan?
Where is yeah, no, I don't know where you make it.
Yes.
Where you produce it. You found the 5-axis CNC.
Yes, we found it at Tashkent.
Tashkent.
CAU University,
Central Asian University.
Yes.
Okay. And my last questions, it's about you really made the rig for testing wheels and bearings, or it's image from
No, it's
AI.
a real one.
No,
Can you show it?
Yeah, имам бана will нені көрсетеді.
Yes.
Дөңгелек.
Презентацияны көрсетші ма?
Жоқ, бізден не сұрап отыр мынаны. Just 1 minute.
This one, yeah, you really made it, or it's AI generated image?
We did it.
Insane, make it.
Yeah, we actually did it with Arduino. So before this competition, we actively used this type of electronics. So it was easy to construct this type of testing robots.
Testing beer, yes.
beer.
And as a result, we decided to choose CMR73C. Yes, this type of beer. Because it has a low.
Okay, thank you.
And can we show you our answers? Yes, aerodynamic.
Yes.
Yeah, this is it.
Yes, as you can see, the air flows very smoothly.
Our 3D model is like totally handmade, so we did it ourselves from zero to this result actually.
And we
Can you open your presentation to the 3D model?
Yeah, of course.
This one?
The last one is
this one. If you want, we can show just
in Fusion.
Yeah, in Fusion. Yes.
Yeah, that's it. So every detail is now made it separately, so you can see the total model and each item.
okay, and open ANSYS one.
Which one?
ANSYS one. No, just open ANSYS.
Answers, yes. Answers.
Yeah, actually they're same.
They're same, yeah.
Okay. Do you have another kind of stress analysis?
Drag analysis?
Strange. Maybe stress.
Yes, of course. Just wait. As you can see, it's peak stress of our topological design.
Okay.
And it's tested in 50 Newton.
Why you put here 50 Newton?
Yes. To make it to be how to say it.
So
more precisely.
Yeah, to more precisely.
Yes.
So, what's the question about actually? Why did we put 50 newtons?
Yes.
Yes. Why you make this kind of analysis for wheel?
I think we make sure that 50 newtons are enough to produce our car, and I mean it's like the average measure, yeah.
No, it's actually 10 times bigger, higher than the real one. Yeah.
To make sure
And
that it's like 100% going to work.
Sorry,
Yes,
your
yes.
time for Q&A is over. We are moving to the
Okay.
next team. Thank you so much.
Yeah.
Okay.
Hope everything was clear. Thank you.
Thank you. And now we have RCR Technica Industries. Are you ready?
Yeah, hello, we're ready.
Okay, great. Can you share your screen?
1 minute. 1 minute, please. So yeah, can you see the presentation? The presentation?
We see, yes, we see it.
Yeah, so everything is okay. We can start.
Okay, so you
Our-
have 6 minutes to present and 6 minutes for the Q&A. So your time for presentation goes now. Good luck.
Okay, so here's our engineering portfolio. And yeah, here you can see car manufacturing process as we talk about. So our cars mostly inspired by real classic cars from real racing series, but bodywork design is also inspired by classic fighter jets. So it has these chiseled lines, but they help aerodynamics because they create vortex generators. And here you can see some photos from development process. And here is our car. Its name is Spitfire. Here you can see first version and example of our livery. And the second version, we made a lot of work with aerodynamics. Good afternoon, everyone. At the first stage, we made upgrade to our car and adding the winter tunnel. We adapt this idea from the Aston Martin Valkyrie and Formula One cars. And yeah, here you can see the parts. So here's the front wing. It is inspired by Formula One cars and slant nose of Porsche 935. And also here you can see the like kind of beginning of venturi tunnel. So the air goes here and goes through the whole car. Here you can see underbody work is mostly inspired by huge diffusers from LMP series and VEC. So it helps to stabilize the air like in the bottom of the car, and so the car stabilizes by itself in the airflow. The rear wings was inspired by the Dodge Charger Daytona from NASCAR. Its walls helps to stabilize the airflow and create just enough downforce to prevent moving the car sideways. And another feature is our rotiform style aerodics inspired by the same race cars. They help reduce air resistance and improve the overall aerodynamics of the vehicle. Also, we changed the trolley design to make it stronger and more stable during race. And yeah, here you can see the venturi tunnel. So the air goes here and makes car more transparent for and makes the car more transparent for the airflow. So it helps to reduce the drag and create more stability. And also creates downforce, so to stabilize the car also. Here you can see first version's aerodynamic architecture, second version's aerodynamic architecture, and the comparison. So drag reduced by 22%, stability raised by 29%, and weight reduced by 8% by cutting like the part of the car. So yeah, here it is.
How you manufacture it?
We'll manufacture it. So the body will be manufactured by model block from STEM Racing, and parts will be printed by really tiny nozzle by ABS plastic. And
Do you have
balls
maybe
will be made from aluminum.
do you have maybe presentation list to show it
Like, what list?
in presentation? Do you have a file to show it?
No, I'm sorry, we forget to add it. We forgot to add it, but we also made all this work. Like we had really, this week we had a lot of tests in our schools, so we were like we had really small amount of time to do all this stuff. We would add more,
What
but
about analysis? Where do you make it?
so first analysis was made in Autodesk CFD, but then the whole program failed. I don't know what really happened. So these lines they were drawn in AI by AI tools, and so the drag, stability, and weight, all this percentage were made by myself and Claude. So mostly visually because like all CFD program, like it just failed. I don't know what really happened. I just couldn't launch it.
Uh, okay, you made design in Fusion 360.
Yeah, whole design made by Fusion, made in Fusion. I can show 3D model.
Okay.
So sorry, I need to share like the whole screen. Oh no, Fusion, just Fusion. And here you can see the model.
Can you show underside?
Here is tetherline guides with special like um, lines that create like a wing form. So it also helps to stabilize the car and makes less drag.
Weight of your car?
Weight of our car is approximately 49 grams by all materials. So the body is made of model block provided by STEM Racing, and other are made by ABS plastic, and also in wheel mounts they are like air spaces inside to make it more lightweight.
Okay. I don't have a questions.
So I can show you some parts. I can show you this like free space for air if you want. So like in this wheel mounts, so here you can see, I'll open it now. So for example, front. Yeah, so here you can see the box that goes inside of the body, and inside of this box, like there are like two holes and just free space with no plastic to reduce weight. Like
So it's empty inside.
yeah, it's empty inside, so yeah, you can see it here.
For the main chassis, what material do you use?
For main chassis, we use this material from model block. It's provided by STEM Racing. It is I don't really remember the whole name, but it's like polycyanic relate or something like this. It's like a foam, but it has like it, but it's also like really strong. It has really high coefficient of not viscosity, but like in physics, it is made with grease letter rho.
How you work with this material, with this
Uh,
foam?
so so with this foam, we'll work by CNC. And with other stuff like made of ABS plastic, we'll use 3D printers.
You found where is you can use the CNC machine
Yeah.
partners or company?
Yeah. So I have I have friends and they have this CNC machine. Like they have their own like factory. They produce their own radiators, and yeah, they have CNC machine. So I can use their CNC machine for all the stuff. And also I have my own 3D printer.
Okay, I don't have question.
So I think we told about everything.
I think yes.
So thank you very much. If you have questions, also you can ask. I'll answer them probably.
Okay, great. And the time for Q&A is also up.
I'm sorry, do we need to exit the meeting?
Yeah, because another team will join later, so you don't have to be here.
Okay, so thank you very much and have a nice day.
Thank you. See you.
Bye.
Sorry, can you give us an access to demonstration?
Yes, of course. Just give me a second. Okay. Can you do it now?
Yes, thank you.
Okay, great. You can start preparing and then we will start the presentation in 2 minutes. I think we can start. So, judges, are you here?
Yes. Yes, I am here.
Okay, so today you will do, Jan team, you will do the technical part, and you now have 6 minutes to present and 6 minutes for the Q&A session. Your 6 minutes will go now. Good luck. Jan team? Jan team, are you here?
Yes, can you give us like 10 seconds? We cannot just have an access to our video.
Okay. Okay, can we start now?
Okay, hello everyone. It's Jan team with you, and now we're gonna show you a little experiment with our car.
Yeah.
Do you see? Oh, I don't know why.
So we did a special experiment with chemical paper. Yes, that's it. So here you can see our car. We're gonna show you in our today's presentation. It's our team, and here you can see the main principles of our work. And let's quickly go to the safety analysis part.
Okay, both models were tested in sim scale using steady state incompressible airflow at 30 meters per second, and force data was related from the stable final part of simulation. In the old model, we had drag force 0.8 Newton, and estimated drag coefficient was 0.4, and lift force was 0.6 Newton. In the old model, we had low drag but high lift reduced stability. But in the final model, we had increased drag by 10%, but reduced lift by 94%. And the final model is more aerodynamically stable because it almost eliminates lift. However, drag increased due to pressure loose around the wheels, front wing, and rear elements. And the next optimization step is reducing wake and pressure drag while keeping low lift. Okay. Next slide. You can see in the slide and innovation.
So our innovation is magnets on the front wing. As you can see, we use neodymium magnets that are very small, very light, and also very strong. Next. That's why we use this plate that's contains both the main part and the front wing, and gives us access to change the front wing as however as we can.
And here you can see our work we did with two experts. The first expert was an race engineer from Moscow Polytech University. We had a meeting with him, and he showed us everything about race engineering, his work, his research work, and he gave us a clear feedback about our safety model and our car itself. And the second meeting we had was with the expert from Zeekr. She was Zeekr ambassador, and she is also a driver and engineer. She also met with us and showed her car, like everything about her car, everything about racing, and we did a pretty good job with the 3D modeling, as she told us.
And in our first version concept, this car had a basic aerodynamic structure, but the main weaknesses were high drag, exposed wheel turbulence, and weak wing geometry, and poor component integration. In the semi-final version, we improved the body integration, we moved toward a more streamlined body, added a teardrop rear pad, and used more aggressive wing profiles. However, the car still had exposed wheel turbulence and cockpit drag, so the airflow was not clean enough around the middle and rear of the car. In the pre-final version, we started solving these issues more seriously. We added front wing deflectors, special front wheel shielding, integrated side pad structures, and aero loop rear wing design. This improved the connection between components, but some problems. But some problems remained. The front spikes had high drag, rear wheel turbulence were still exposed, and the cockpit elements were not fully integrated in his body. In the final version, combines stronger ideas from the previous iterations. The main breakthrough is total component integration. The front profile, side pads, body, rear wing are now designed as one connected aerodynamics loop. Okay, to the next slide. Okay,
final design is as you can see, the final design contains very round back wing and very aggressive style of the front wing, same as the main body, and we are planning on having the different type of front wing and give our car more space to have less weight. Next. manufacturing. We designed our car for good manufacturing. We use Bumbleup A1 as a 3D printer and used PLA filaments instead of other filaments because it is good for sim racing. And the border thickness, the wall thickness is 0.2 millimeters, and the
Sorry, your time is over for the presentation. Now you have 6 minutes for the Q&A.
Okay.
Guys, can you show us 3D model of your car?
Já usa Twitter?
One second.
No, guys, I mean, which software did you use for modeling?
In real life or in the fusion?
You mean the step file or like this?
No, I mean step file. Can you open it?
Yeah.
Может, ты скинешь ссылку на этот покажу?
Нет, я через прямо открываю.
Окей. Кинул?
Чатик закрепи стоит.
I have one question to your your 3D model. Where is the final 3D model that you sent to the organizers is correct, right?
Yes.
Yes.
Yes, it is.
Do you know that you should make like a small rings for the table of the
Yeah.
racing table?
Yeah,
Where is your rings?
I designed this exact holes for different type of bearings because we don't actually have right now the bearings that are usually used in sim racing, and that is why I designed it for more bigger bearings for it to be able to move to. Yeah.
A few days ago, 1 week ago, or a few days ago, there was a meeting with us with how to say with judges, and we say that you should make a 3D model that tomorrow we will assemble. We will assemble by this 3D model. Really physical your car in the physical type, a real car with bearings, with for example from aluminum or balsa wood block, and it will be ready to run, really ready to run. For example, if tomorrow we will go to the Singapore, we should just put your car to the table and it can run. So why you send us 3D models that for example for the 3D printing?
I'm so sorry for misunderstanding. We misunderstood the task. Can we maybe send within a few days or maybe today
Okay.
another? Thank you so much for understanding. Thank you so much.
And another about the material. What kind of material do you use for making your car?
PLA filaments, PLA plus filaments.
Do you have any kind of analysis why you choose PLA?
Yeah, first of all, PLA filament is recyclable and it is very strong and it can handle big air pressure.
Oh. PLA is not strong. It's a very weak type of plastic, so I don't know. Okay. About the how do you make open the machining plan? If you have a plan of the making manufacturing, how you will make manufacture your car?
In the future or like
No, you have in presentation manufacture plan of manufacturing.
we got 3D modeling. in the
No,
presentation.
not 3D model, manufacturing plan. For example, tomorrow, for example, we will for example, print on 3D print. Main part we will cut on the CNC machine. For example, I don't know, maybe front part we will make from the carbon fiber using vacuum infusion, something
We
like.
actually are going to present it tomorrow with enterprise portfolio, because there we're going to show like our future plans, and there we already assembled everything related to that. So can we show it
Yes,
tomorrow?
but it is technical part, and when I asked you and we made a video, we asked, please, we need your 3D model, we need your manufacturing plan, how you will manufacture it, and we need analysis, and maybe about design, how you get this design, or your idea and your inspiration. And our main goal was prepare and choose the main team that is ready to run tomorrow. But if you don't have a plan to how do you make your car and how do you will manufacture it, I don't know. Do you have any kind of analysis, maybe? Structural analysis, physical, maybe aerodynamics? Okay. What is it shown here, and which software do you use?
We used SimScale for this 3D analysis. In the three screenshots, we see the stress analysis and
Sorry, time for Q&A is up. That's it.
Okay, but there is no stress analysis there, only aerodynamics analysis of the, no, maybe drag coefficient.
Stress analysis, like static analysis.
Yes, analysis of that your car is, for example, in the future it wouldn't break in this, for example, first start. Like analysis of the material for the dynamic or the maybe just pressure, maybe static pressure. That shown in the approved that your choosing your materials is good enough. For example, for PLA plastic, I don't know, ABS, maybe carbon fiber, I don't know which material you choose. You just should approve it that this is okay for your pressure, because your car will go about 25 or 26 meter per second. It's very fast, and it should be stopped by the in the end of the table. It just be stopped, and it shouldn't be disassembled and broke. So it should be strange enough, and you should approve it to judges, to us, that it's you choose a good material. Okay.
Okay, I think that's it for the team.
Okay, thank you so much for attention. We can show our future plans tomorrow and stand the model within a few days. Thank you so much.
Thank you. See you.